So this video is going to be for Chemistry 1211. We're going to go through sections 4.4 through 4.8, mainly focusing on Lewis structures. So Lewis theory is a theory that says that atoms form chemical bonds by sharing electrons to get the configurations of noble gases. We call this the octet rule. So the octet rule is that atoms tend to lose or gain or share electrons to obtain a set of 8 valence electrons. If they're losing or gaining, then we say that that's an ionic relationship. If they're sharing, that's covalent. And we can remember that because sharing is caring. Caring starts with a C and covalent starts with a C. So sharing is covalent. And we're looking for 8. There are some exceptions to the octet rule I want to point out. Hydrogen and helium have a max of 2 electrons. They can't get more than that because they're very small. Helium, the 2 electrons in helium are called a duet. So instead of an octet, we call it a duet. Beryllium is a metal, yes, but sometimes small metals like beryllium and aluminum can do covalent bonding stuff. You may see that pop up in different cases. If you do see beryllium and you need to draw a structure for it or assume that it's doing any sort of covalent bonding stuff, then you can only give it a max of 4 electrons. Boron can hold a max of 6. And these are just because these are very small atoms and they don't have a lot of protons, so they can't really hold on to a lot of electrons. There's another bit of exception here, which is that any element, period 3 and below, like literally below, like down, so like period 3 and up, so 3 plus essentially, can, if needed, expand their octet, which means they can hold more than 8. So let me write that there, and then greater than 8. So they can hold greater than 8 if they need to. And we'll talk about situations in which it'll be very obvious that they need to, and then situations where it's not so obvious that they need to do this, but they will do it to get a more stable structure. So we'll start with Lewis symbols. Lewis symbols are just basically how many valence electrons are around an atom, and we just put those dots around the symbol to indicate the valence electrons. So you will put your chemical symbol in the center, and then you will pretend like there is a box around the chemical symbol. And we will place our electrons around the box. We're going to put 1 electron on each side before we pair them up because electrons don't like to be together, right? So you know how we do orbital diagrams. We put 1 electron in each box first. Same thing is going to apply here. So my first electron, you could pick whatever side you want to start on. It does not matter. I like to just start at the top. So I'll put my first electron at the top. Then I'll put my second here, and I'm just going to go around, leaving space for a second one. Now, if I have 4 electrons around, it would just be 1 dot on each side. As you can see for carbon over here, 1 dot on each side would be 4 valence electrons. If I want to keep going, I would put my 5th one here. I would put my 6th one here. I put my 7th, and then I would put my 8th. So 8 would have 2 pairs around it. Notice that helium has those 2 dots on the same side. This is important for helium because we're trying to say it's not the same kind of 2 electrons as like beryllium and magnesium. These electrons are creating that duet. So we just put them together for helium. So that's why you'll see that difference. And then remember that your valence electrons just go across the tall groups. So your valence You could do the whole electron configuration if you want, but it goes across 1, 2, 3, 4, 5, 6, 7, and then technically 8 up here, but really remember that only 2 for helium. So you could find the valence of anything in a tall group pretty easily just by counting across the top. We're really only going to be dealing with tall group stuff for Lewis structures, so you won't have to worry about valence for the middle. So for ionic compounds, which we'll just visit briefly, how would we draw the ionic compound? Well, a Lewis structure is, traditionally, we're going to talk about Lewis structures only for covalent stuff with sharing. But if you are drawing it for ionic, you can show it. You cannot draw a line between it to share if that's what you're thinking. But we can show electron movement. So we can say that the electron from sodium is going to go onto the chlorine. So sodium will be losing to become a cation and chlorine will be gaining to become an anion. So this electron I can highlight in red just went to the chlorine. And so what would the Lewis structure of sodium chloride look like? This. No line connecting them. They're not sharing electrons, but they are just hanging out together. So they are near each other. Sodium lost that extra valence electron, so technically its new shell would be the one below, which has 8, but we're not going to just put the 8 around sodium because that is a little confusing, so we just leave it with nothing and we put the little plus sign there. We're going to be focusing on molecular compounds or covalently bonded compounds for our Lewis structures. We represent them with a couple of different things. With a Lewis structure, you've got a chemical symbol showing the element. We have a line, and each line I want you to think about as being 2 dots that we're connecting. So 2 electrons in a line. This line is a bond. This one is a single bond because it is just one. Then we have electrons represented as dots by themselves. This would be representing a lone pair of electrons. This is unshared. So nitrogen is not sharing these electrons with hydrogen. The ones in a bond are being shared. So the line is called a bond. And these are shared electrons. So it's shared between the hydrogen and the nitrogen. So if we were to go counting electrons here, we would say nitrogen has access to 2 that it's keeping on its own, 2 that it's sharing with the left hydrogen, 2 that it's sharing with the right hydrogen, and 2 that it's sharing with the bottom hydrogen. So nitrogen has access now to 2, 4, 6, 8, which is that octet. So nitrogen in this structure has access to 8 valence electrons, even though they're being shared. So that means it's satisfied its octet rule. It's happy. Then the hydrogen has access to those 2. And remember, hydrogen has a max of 2. When it has 2 electrons, it looks like helium. So it's good with that. So each hydrogen is also satisfied for its rule, which is technically not the octet rule, but if you were just to ask a question like, hey, is everybody behaving by the octet rule here, you would say yes. Technically hydrogen is an exception, but it is full with just 2. So these are 5 steps to drawing Lewis structures. If you may have learned this before, do whatever you do that is working for you. If you find that what you're doing is not working for you, I recommend that you come back to these steps. I think that if you were to use these steps 10 times, by the time you finish these steps, then you would have learned the steps. I'm going to make one alteration, maybe 2. I'm just going to go through it. Make one alteration. We're going to complete octet. We're not going to complete octet on centratum. This step 5 should read, sorry, I messed up typing this, should be the check octet on all atoms. You shouldn't have to check on your outer if you have given them, if you follow the steps, but just to make sure we got it there, check octet on all atoms. So, go through these steps. Please do not take off and just try to do it without, look at the steps one time and then try to do a bunch of examples. You're going to get yourself very confused. If you follow these steps, you will get your Lewis structures correct. And then we're going to be adding on to these steps to determine if our Lewis structure is actually a good structure or not. Because you can follow all the rules and still not be a great structure. And we'll talk more about that a little bit later. So let's try using these steps to draw a molecule, CHCl3. And again, these steps I have down here are just a little bit different. So check octet. And then I think this step was actually moved to step 4 when I rewrote these. So let's go through it. Determine the total number of valence electrons. For CHCl3, we have 1 carbon. So I'm going to put the number of atoms here, and then I'm going to multiply the number of atoms by the number of valence electrons that element brings. Carbon has 4, because if I look at the periodic table, carbon is in group 14, so it has 4. We're also going to need to grab hydrogen, which has 1, and chlorine, which has 7. So next, let's do hydrogen. Oh, and I like to add them up, just sum it up over here. Get the product of that multiplication. I have 1 hydrogen. Hydrogen has 1 valence electron, so hydrogen brings 1 total to the table. And I have chlorines. I have 3 chlorines, each with 7, so they bring 21 total electrons to the table. Then we're going to add all these up. Now you could just do this all in your calculator or in your head. We have 26 total electrons that we have to give in our structure. That's our step 1. So step 1, 26. Now it says add or remove electrons to address overall charge. If this thing said -1 here, we would have to add an electron, so it would be 27. If this thing said +2 here, like a polyatomic ion, we would have to remove 2 electrons, so it would be 24. So just pay attention to if you're dealing with a polyatomic ion and its charge, you would just alter this step by adding or subtracting electrons from this total. But for right now, we know we have 26 we need to give out. Notice that I didn't start by adding any dots or anything to my carbon, hydrogen, chlorine. If you are doing that method and it's working for you, great. If not, follow the steps here. We're going to arrange the symbols of elements to show how the atoms are bonded together and connect them with single bonds. We want to try to connect everybody to a center. The least electronegative should go in the center, except hydrogen always has to be on the outside. So if we go to the periodic table, least electronegative is going to be farthest to the left, essentially. So we have hydrogen cannot be in the center. So carbon versus chlorine. Now, if you're looking, you're like, hey, well, chlorine is lower. For this one, just focus on whoever's furthest to the left. So chlorine likes to be in the middle because it likes to have 4 bonds around it. Nitrogen likes to have 3 bonds, oxygen 2, and fluorine, everybody in this family is 1. So just so you know, if you see carbon, silicon, it's probably going to be that they're in the middle. You'll get better at just kind of telling who should go in the middle by doing a little more practice. So what we're going to do is we're going to connect them with single bonds. A single bond is going to be a line. So a single bond is 1 line. And then also another thing to note is that you will try to make molecules symmetrical when possible, unless you're told otherwise. So for example, I wouldn't say C, Cl, Cl, ClH, when I could say C with 4 things around it. So try not to make it all like in one long line. And again, there's not really like a specific reasoning. It's just as you go and you look at a bunch of these and you do practice, then it'll help you know kind of what looks right. So I'm going to put just I got 4 things I have to put around my carbon, 1 hydrogen and 3 chlorines. And it doesn't matter where I put the hydrogen. I could have put it on the left, the right, the bottom, whatever place you want to put it. It's up to you, kind of like Bob Ross. a little bit more strict than Bob Ross's painting rules, but you can put it where it moves you. Then step 3 is complete the octet of atoms bonded to the central atom by adding lone pairs of electrons. So we're going to be adding a lone pair. A lone pair is 2 dots. We're going to complete the octet on the outer atoms first. So let's look at our outer atoms. So how many do they have versus how many do they need? Hydrogen now has access to 2. Remember, each line represents 2 electrons. Hydrogen is actually totally good with 2, so we can't add anymore. Chlorine, though, only has 2. Chlorine is not good with 2. It wants 8. So I need to add 6 more. So I'm going to add that in dots. Pairs of dots. 1 pair is 2. 2 pairs is 4, and 3 pairs is 6. So now this chlorine has 2, 4, 6, 8. I'm just going to kind of copy that as I go through my other chlorines. Don't worry about how many valence electrons they started with, how many they have right now. Just fill up the outers until everybody's happy. It's going to make it a lot faster for you to draw these structures, and it'll make it a lot easier. Notice that I didn't subtract out the bonds yet. Like, I'm not doing all of that mess. I know that you may have been taught that before. The textbook may show you, like, hey, subtract out the bonds and then do this, and lab also may show you that. I think it's easier just to fill up my outsides and then do a count. And then I can always erase if I added too many. So now we're going to do a count. Compare the number of valence electrons in the structure to the number that we got in step 1. So now we're going to see, do I have 26? I have 2, 4, 6, 8. Now here's why I like to add up, just go ahead and put 8 on the outsides first. I have 3 sets of 8. So that's 24. It's easy to count that. I don't have to count 2, 4, 6, 8, 10, 12. Like, I just go, oh, I know I have 3 that I just gave 8. So that means it's 3 times 8, which is 24. And then I have extra 2 right there. So that's 26. So I'm good. I've added all my electrons. All right, now we're going to check the octet, which is actually what I would like to be part of step 4. Oh no, sorry. If you have leftover valence electrons, you can put them on the center. So if for some reason we had 28 left to give, we could stick them on the middle if we had room to do that. Carbon can't hold more than 8, so we couldn't do that. But if it were sulfur or something, for example, and we had 28, we'd put dots on the middle. But the next step 5, is going to be to check octets. So we're going to check our octet. Chlorine, this is also easy if I went ahead and fill up my outers. I know that the outer ones are happy, because I just made them happy, right? I just gave everybody their 8. Then let's check the carbon. 1, 2, 3, 4 lines. Each line represents 2. So when we count a line, we can count by 2s. 2, 4, 6, 8. So carbon is actually all good. If everybody's happy and you've given out all your electrons, we're done. If for some reason the carbon wasn't happy, we would have to take away some electrons from the chlorine and make a new bond. That's when you would get any single bonds or any double bonds or triple bonds, would be by moving electrons around to satisfy a center. Don't ever add electrons as bonds. Always put single bonds around, connect everybody, add as dots, pairs of dots. Then once you have all the dots in there, then we can move electrons around and make double bonds and triple bonds. So we have a double bond. If for some reason we needed that, would be 2 lines representing 4 electrons total. And then we would have a triple bond that would be 3 lines representing 6 electrons. So each line represents 2, single, double, triple. These are all just bonds. And we can make doubles and triples if we need to satisfy the center, if the center doesn't have enough, by just erasing pairs from the outer and making more bonds to the center. It'll make more sense once we do an example with it. But this is my final structure. Everybody's happy, and I've given out my 26. We're going to stop it there for what we're learning for right now, and we're going to go into in a few slides of another analysis to do afterwards. But hopefully that was a good example. So here's what happens if we have a double and triple bond. So let's say we're going through and I've given out, they're giving away my work here. So let's say we're going through, we have this structure here. We have CH2O. So C, 2 H's and an O. Let's say we've given out all our electrons, and now we're at step 5 where we're checking the octet. Now, if we look at our octet, oxygen is happy. It has 2, 4, 6, 8. Hydrogens are happy. You cannot add dots to hydrogens, remember, because hydrogen can only have 2. When it has a line, it already has 2. But carbon has 2, 4, 6. Carbon is not happy. Let's put it in red. Carbon is mad. So we have to satisfy the carbon. So how can we make the carbon have 8? We don't have any more electrons left to give. Let's say we checked our number of valence electrons and that's all. We don't have any more. So what we can do is we can take 2 electrons, any 2 electrons from an outer atom, and we can move them to a bond. If you move them to the carbon, then the oxygen would be sad and the carbon would be happy, but then the oxygen would be sad, and that wouldn't work out. So you don't want to move them to the other atom as lone pairs. You want to move them to the other atom as shared. So both of them still get the benefit of counting those 2 as part of their 8. So we will move to, so I say erase and replace. We're going to erase these 2 and we're going to replace them as this line right here. So this line used to be those 2 electrons. And in this image, they kind of just moved the other electrons over a little bit, but they're still, they're the same thing. So let me just color code them so that you're not super confused. These blue ones, they just got shifted over. And these ones are purple. Just so we could show how electrons are repelling each other, kind of, but you don't have to worry about doing all that. But the red line is where those 2 red electrons went. And now the carbon is happy because it has 2, 4, 6, and 8. And I did not actually add any electrons. I just moved them around in the structure so that everyone has their 8. So hopefully that makes sense as to how we would get our double or triple bonds. So let's take a look at ozone. Ozone is O3 and oxygen is O2. By the way, if you wanted to pause and just try to, you wanted to pause and just try to draw the Lewis structure of ozone, O3, and oxygen, O2. You can pause and try to do that, pretend like you didn't see the answer there. Draw those Lewis structures. If you drew O2, if you're wanting to continue working on that, just pause it real quick. If you drew the O2, you should get double bond and then 2 lone pairs on each oxygen, by the way. Now, ozone looks like this. Now, maybe you drew your double bond on the left oxygen, or maybe you drew it on the right oxygen. But actually, both are correct. And so we call this resonance. Resonance is present when 2 or more Lewis structures can be drawn with the same arrangement of atoms, but a different arrangement of bonding electrons and lone pairs. So if I can just pop my electrons around and share them so that both oxygens get to experience the double bond, basically that's what really happens in real life. The electrons they just hop around and they go back and forth and back and forth. They resonate, and that's what gives us resonance structures. So resonance structures can stabilize a molecule. It can make it a molecule that might not. So ozone is not very stable. This single bond right here is really easy to break. And so actually that's a little more stabilized with this resonance. It's because the electrons are delocalized over all the atoms. And so the atoms, everybody's sharing the extra burden or extra load of those electrons. Everybody's getting access to them because they're being rotated around. It's a little more even, and that makes it more stable. So if you ever have a choice of where do I put a double bond here? Do I put it on this side or that side? And it's literally the same element, same outcome, but just maybe like flipped different sides. So like if I had an F on this side, I wouldn't have resonance by trying to make it a double bond here, because fluorine is very different in its behavior than oxygen. But because these are both oxygens on either side, then we can do this and we can have this resonance. So if you ever have a situation where you have this resonance, when you're asked to draw the full structure, you should show all options. And we do this by drawing this little back and forth arrow between the options to show that actually it does go back and forth between these two. These electrons are moving back and forth between those 2 structures. And so oxygen has 2 equivalent bond lengths. So I want to just kind of show you why this is kind of weird. So we should expect that a double bond between O and O is about 121 picometers long. And a single bond between O and O would be 148 picometers long. So which bond is longer? Single bonds. So as you increase your bond order, which is what we're going to call this, so bond order, they actually define, yeah, bond order is the number of bonds. So bond order for single would be bond order of 1. And for double, it would be a bond order of 2. So we expect a lower bond order to mean a longer bond length. It's actually also weaker. So bond order of 1 is a weaker bond. It's easier to break it because it only has 1 point of connection. Bond order of 2 is stronger than 1 because there are more points of connection. A bond order of 3, for example, would be like a triple bond, and it would be the strongest of these 3. All right, because it's got 3 points of overlap, and it would be the shortest. Now, a triple bond between oxygen doesn't exist, so I'm not going to draw that there, but like longer is bond order of 1, longer and weaker. Shorter is stronger. So like a closer connection is stronger. So we would expect ozone that has a single and a double to have one side that was 148 and one side that was 121. But actually, both sides are 128, which is in between double and single. So it's kind of like a bond order of 1.5 kind of. And it's not exactly, there are other ways to calculate bond order. So if you move up into higher levels of chemistry, you may learn actual formulas to calculate bond order, but we can think it's in between 1 and 2, right? It's not quite a single bond, not quite a double bond. And that's how we know the resonance is really happening, that the electrons are actually bouncing around. We're not just rotating the molecule around. Because we don't see a 121 and a 148. We see a 128, which is like an elongated double bond, which is weird. So that's how we know the resonance is actually happening. So bond energy is the energy needed to break a mole of bonds in the gas phase. A mole is just an amount of particles. And so basically the bond energy tells us there's like a sweet spot of bond length. So distance between the nuclei get to this really low energy section here. This is what we call the bond energy. That's where it's going to settle. So if you had a marble and you dropped it on either side, it would settle at the bottom at the lowest potential energy. Too far apart, no attraction, increasing attraction. We get to a sweet spot of attraction. If you start to get too close together, your nuclei start to repel each other. And so that's no good. So there's a sweet spot of comfortable bond energy and bond length. And that is where we get that bond energy. The bond energy is based on what's the potential energy at the bond length that we see. Bond energies increase as bond order increases, meaning that it takes more energy to break. This is what I was saying. You can think about bond energy as a relationship between bond strength. So the stronger the bond, the more energy you need to take it apart. Okay. And then lastly, for Lewis structures, we're going to talk about formal charge. A formal charge is, let's say I draw 2 Lewis structures and actually all the octet rules are met, but they're just different structures. How do I pick which one? So if we look at these 3 options, you can draw 3 different versions of N2O by just kind of moving electrons around in different ways. If I said draw N2O with N in the middle, so we're not symmetrical here, we have N in the middle, you might have drawn this. This is totally valid. Everybody's got a set of, got their octet. That's the right number of electrons. You could have drawn this. Totally valid. Or you could have drawn this. Totally valid. Formal charge is going to allow us to check to see which one is probably more likely that it's actually the real structure. Quick note about formal charges. Formal charges are not real. They are not real charges. They are only the way that we can judge Lewis structures. Is an easy way to judge Lewis structures. There is a controversy in chemistry with formal charges, like whether or not they're good things to use. But we still are using formal charges here to judge our Lewis structures. But if you go farther along in chemistry, you may learn that like in some research that formal charges actually don't really mean anything to your research. So just FYI. But they are not actual charges. So when we are adding formal charges, we are not doing ionic stuff. We are not talking about bond polarity or anything like that. We are just saying we're counting up the electrons that are assigned to an atom. Okay. I have an easy way of counting formal charge, and the textbook has a way of counting formal charge. So formal charge is number of valence electrons minus the number of electrons in lone pairs on the atom minus 1/2 of the number shared. Here's an easier way. Formal charge equals valence electrons for that atom minus dots minus lines. Okay. So if we look at that, let's look back at our N2O. And I don't want to spoil it with the answers in the next slide. So let's go back up here. Gonna copy this and let's do it together so you can see instead of just looking at the slide. So let's do the formal charges for these three. I'll do one and then I'll let you break and do the others. I'll do the middle one and let you do the other ones. So valence electron for this nitrogen. Valence electron is 5. Minus how many dots? 1, 2, 3, 4, 5, 6. Minus how many lines? 1 line. So formal charge of 5 minus 6 is -1, minus 1 is -2. This would have a formal charge of -2. You could write a little -2 next to it. I think if you're doing this in homework, it would kind of circle it like this for you. But however you want to write it, that's fine. Not an actual charge, by the way, not a charge. We're not talking about ionic compounds. We're talking about covalent compounds. This is just a way to judge Lewis structures. Okay, just trying to get that out there. Look at this next one. The valence electrons are going to be 5 also for nitrogen again because I'm looking at the periodic table. We have no dots, so no dots. And we have 1, 2, 3, 4 lines. So 5 minus 4 is +1. Okay, so this one has a +1 formal charge. And then let's look at the oxygen. Oxygen has a valence of 6 minus dots, 1, 2 dots, minus lines, 1, 2, 3 lines. Equals 6 minus 2 is 4, minus 3 is -1. Yeah, let's say that does not work. Notice that the formal charges all add up to the overall charge. So N2O is not a polyatomic ion. Overall charge for this is 0 because there's nothing written at the top right like a polyatomic ion. So formal charges all have to add up to 0. So we have -2, +1, and +1 all add up to 0. So formal charges add up to overall charge. That's another way to check your Lewis structure. If you do formal charges and it's not matching up, your Lewis structure might be off. Now, the goal get formal charge as close to 0 for as many atoms as you can. Because when a formal charge is 0, that means that atom has the same amount of electrons around it, kind of like it's responsible for, why are we counting the bonds as one, or why is it counting as 1/2 here? Because if there's 2 electrons in the bond, one of them is kind of nitrogen's responsibility, and one of them is oxygen's responsibility, right? So oxygen's really only responsible for half of that bond. That's why I'm counting the bonds just as one. So if the valence is equal to the lines and the dots, then the number of electrons that that element is used to having around it is the number that it currently is responsible for. And that is good because I'm used to having 6 valence and I've got 6 around me, like responsible, that I'm kind of responsible for right now. And so I know what to do with those. So see if you can do formal charges for the left and the right one and see which structure would be best. Why don't I give that a pause? All right, so for formal charges, for the left one, for option A, you should have gotten the left nitrogen as 0, the middle one is 1, and the oxygen is -1. We did this one. Oh wait, they changed it on me. So they did the one on the right. They switched it. So the one that I did in the middle was the -2 +1 and +1 and +1. And then the one on the right you should have done was -1, +1, and 0. So already A and B look better because more of them, we have more zeros. The one I did has no zeros, so that one's not as good. So let's throw that one out. Now I have to make a decision. If I have to put a negative formal charge on somebody, is it better? Because the middle nitrogen is going to have a +1 no matter what I choose between A and B, right? Is it better to put a negative on oxygen or a negative on nitrogen? I want you to think about that in comparison to where they are on the periodic table. Who is more likely to be okay having more electrons than normal? Maybe you're thinking oxygen. If so, you're right. Because oxygen is more electronegative. It likes electrons more. So it's okay with having some extra electrons around it than it normally should have. So if you have to pick who gets a negative, give it to the more electronegative atom. So any negative formal charges should be on the more electronegative element if you can help it. All right, so we can add that back. If you go back to the Lewis structure steps, you can make a step 6, check formal charges. Make sure they're as close to 0 as you can get. Okay. And then if you have to do exceptions to the octet rule, we talked about that before. Aluminum is also one that forms an electron deficient molecule if it even does. I want you to consider aluminum to be a metal for this class, but you may see it do some crazy stuff. You won't see it, I don't think, in this class, but in the future you may. And then some atoms can have more. So look at sulfur. It's in period 3 or greater. So it can have more lead than 8 if it needs. In this case, it needs to because it's literally bonded to 6 Fs. So sulfur hexafluoride has 2, 4, 6, 8, 10, 12 electrons around that sulfur. It's okay though, because this sulfur is bonded with fluorine. So if you are bonded with something that's really electronegative, like fluorine, oxygen, fluorine, like all kind of around that top right corner, imagine that the fluorine is pulling these electrons really close to it. So the sulfur is not actually, yes, technically responsible for half, but really the fluorine is cogging all the electrons. And so the sulfur is not really having to take on a lot of that extra negativity, so it's okay. So if we have to do this expanded stuff, it's better if we're doing it with something like fluorine, oxygen, chlorine, and you'll see that happen. And then also we'll only do it if that gives us a formal charge of 0 for or a better formal charge, closer to 0. And so we're not going to be expanding the octet. We're not going to be just adding in random bonds and things unless it gives us a good formal charge situation, or unless we have to, because the structure literally is just put 6 of these Fs around an S. And again, all nonmetals in the 3rd row and below can have an expanded octet. So period 3 plus, period 3, period 4, period 5, etc. And here are some examples where you might see that. And then again, they'll do it when they're bonded with something strongly electronegative and when formal charges are good because they do it. And then sometimes you may have a weird situation like this where we just have an odd electron. So nitric oxide only has 11 valence electrons. It's not an ion. So we can't remove the electron or add more. And so when we do this Lewis structure, we just get a nitrogen that only has 2, 4, 6, 7. It doesn't have an octet. So we just don't have enough for it. we call this a free radical because it has an unpaired electron here. It's going to make it super unstable, really reactive. But look, its formal charges are great. Like the nitrogen is 5 minus 1, 2, 3, 4, 5. So it's good. Oxygen is 1, 2, 3, 4, 5, 6, which is what its valence is. So it's reasonable that this can happen. I mean, we don't have an octet on nitrogen, but we don't have enough electrons. So you might get into a situation where that's just what it is. Double check, though, that you have an odd number because you should not have that happen very often. And then just as a quick little nod to like why we even talk about structure and stuff. So certain covalent bonds vibrate in different ways. So covalent bonds are not rigid. They vibrate, they stretch. Carbon dioxide, for example, is shown here. And carbon dioxide, these bonds can do different types of stretching. And this can hold energy. So this is why carbon dioxide is a greenhouse gas. It's because those bonds, there's actually double bonds there, so they can hold a lot of energy. They can stretch and they can bend and vibrate, and that can hold energy. And then when they do the stretching and bending, they can also release energy, which is where we get the greenhouse effect from. So just as a related to real life bonding situation. But that's it. So this video will count for any future classes where we're doing Lewis structure work.